Now let us look how we're gonna modify our code to measuring the time delay. So usually the time analyzer that we have done on the Quartus is done through only this FPGA here, this chip. It doesn't include all the other traces from the switches to the LED light. It doesn't include those. So one way we can do that is copy all the signals to the general purpose input-output headers. So let me explain generally how we're going to do it. For example, if you want to measuring the time delay from input x0 to output majority detector. So here, one way to look at it, for example, here is our FPGA chip. So all these are the pins from the FPGA that we have done on the pin planner, and then we assign one pin to, for example, to X, W, and count and majority detector. Let's say, for example, those are the pins, and then you go and assign them on the pin planner. And down here, for example, we have our, here we have our switches. For example, here we have X0 switch, and this is the trace. For example, it takes to go to the FPGA pin. So, for example, this the trace here, this wire trace is 2.5 centimeters, and it have roughly 200 picoseconds the delay. And then here we have our LED lights, roughly LED lights. Let's see, we have a majority detector, and this one is connected, for example, to this pin here, and it's have its own traces and delay. So, but here on FPGA, the time estimation is done only through here. It exclude all this one. It doesn't include all these delays. So we only get the delay from here. But and then it's not possible for us to put probes to here and here to start modeling from input and output. That is not possible. So we need to copy those signals to our general purpose output headers. For example, here, those are general purpose output. For example, so it have this kind of pins. So this is our general purpose input output. And then, so one way to do it is to copy those signals and send it to our output headers, GPIO out. So this will have its own delays inside here. For example, the conversion, for example, here is nanoseconds to convert this signal here, for example, to this pin here, and the other one, that is the output of majority detector. And then the other one, for example, let's say 7 nanoseconds here, and it's converting here, and it's going through here too. So now it make us possible to measure with probe. So we can have one probe from in here. This one is input, which for example is x0. Now it make possible that we have a probe, so we can measure. For example, if you have a probe, let me just take another color here. Let's take first blue for inputs. So if you have a, so we have a one probe here, and then we're measuring the delay. So for example, this is we have a scope here. So that is the input. We are measuring the delay, and then let's take red color for the output. So this is for example is a probe, and then we are measuring the signal to here. So what we're gonna measuring now, what we're gonna measuring here is the difference of the delay time. For example, we're gonna measuring the delta t, which is the output minus input. We will not get exactly estimation that we have on FPGA, because the FPGA is going to give delay, for example, for this one, and they're going to give delay for this one, and then we need to take the difference out of this. So because it's not possible, if we could measure direct from here to here, that we're going to get some actual delay. But so we need to keep in mind that this is what we expect. We're expecting the difference of output and input, not directly delay from input, for example, to output of the red light. So this is kind of a general idea. So we will go to Quartus and start encoding this and explaining how we can copy those signals and send it to the GPU outputs. And then this headers here, they have usually 3.3 volts, and then we're gonna measuring half of the signal. So for example, usually is the signal will look like this. And then you have for example, this is input, and then you have an output. So usually we're gonna trigger it at half of the 3.3 volts, which is almost 1.65 volt. So you're gonna trigger from here and measuring the difference of here. So this is how we're gonna do it. But first of all, let's go to the code and add those two signals and starting implementing. And the one thing I need to mention, we will not use the same switch, since this slide switch have some noise, and this will be captured at the scope. So we need to use like with a Smith trigger, which we have the debug. So let's code this in the next video.